Hello friends, in this session we will see the concept of controllers, we will see their types, we will also see their advantages as well as disadvantages. Along with that, we will check out the interrelation of them with compensators. Let us begin. Yes. So speaking about controllers, we have basically two types of controllers. First one is a series controller and other one is called as a parallel controller. How do they look? Let me tell you. For example, let us say you have a plant. This is a negative feedback, right? This is R and this is C. Reference input, controlled output, feedback, right? Now, if I have a block here in series with the plant of controller, then it is called as a series controller. Okay? You have a plant, you have an output C, you have input. This is R, right? And out of feedback. Now, what I'm saying is, if I have one more summing block here, negative feedback definitely, and I have a controller which is in feedback in this way, then we say that it is a parallel controller. Okay. Now, what will I do is, in order to understand it in detail, what will I do is, I will take a transfer function. I will take a transfer function which is, let us say, g is equal to 1 upon s minus 1. Okay, I will take this particular transfer function and try to add it with all the different types of controllers and try to check what happens to their output and what happens to the stability of the system. Okay, so this is a transfer function we will be using throughout this particular lecture. Okay, so the first topic, let us begin. The first type of the controller is the proportional controller. Let us talk about that. Proportional controller is also given by kp. Remember, this is not same as error constant kp. Okay, this is kp, this is different. Error constant kp is nothing but position error constant, right? But this is not that one, this is not that one, remember that. Okay, yes. Now, if we think of a proportional controller, how does that look? This way. Kp, got it? Yes, right. Now, if you see this transfer function, it is only g. This is an open loop transfer function, right? Definitely, it is unstable transfer function, open loop transfer function. It's okay. What I am interested in it, let us try to see. I want the closed loop transfer function of this particular one. So let me just replace this plant by its own transfer function. Okay. Now let me find the closed loop transfer function. Closed loop transfer function. How does that look there? That looks like kp. Yes, definitely these two blocks will get multiplied, so you get kp upon s minus 1. Right. Now this is your open loop transfer function. So open loop transfer function upon 1 plus loop gain. Again same thing, 1 plus kp upon s minus 1. Is that correct? Yes. So if you just see, then this becomes equal to what? Kp upon s minus 1 plus kp, and yes, denominator s minus 1 and s minus 1 will get cancelled at the end, right? This is the equation we get. Let me call this as first equation. Now, from this equation, this is the characteristic equation, s minus 1 plus kp equal to 0. If I do, this becomes characteristic equation. So you got s equal to 1 minus kp, right? What do you understand now? What do you understand now? You have seen that if, for example, let us say my kp, which is there, it is, let us say, equal to, if my kp is equal to 2, then what is going to happen? S is equal to 1 minus 2, which is equal to minus 1. System will become stable. What my point? System will become stable. On the other line, if I think of, let us think of an input and then try to find the output. If you see here, let me consider unit step input only. Okay, unit step input, no problem. So the output C of t is going to be what? Yes, definitely Laplace inverse. Laplace inverse of what? Laplace inverse of this function, whatever we have got, this function. Laplace inverse of this function, kp upon s minus 1 plus kp, right? Yes. Now, what will I do is, this inverse Laplace of this function is nothing but, if you remember this you will get kp into, kp will come out and this becomes e to the power minus of kp minus 1 into t, c of t, correct? This becomes the inverse Laplace transform. Why? You have used the first shifting theorem, right? Because 1 upon s plus k is there, then it becomes e to the power minus kt, right? Similarly, if you just think of minus 1 plus kp, then minus 1 plus kp, negative of that will become 1 minus kp, 1 minus kp only, which is nothing but the same thing, same as this one. This will be plus anyways. Getting my point, right? This is a simple transform, Laplace transform. You must be aware of this one. Okay, anyway. Now, what will happen now if you see? What will happen if you see? Definitely, at as t progresses to infinity, no, what has happened? Your error became zero. Error will become zero. That is what is there for sure. That will happen. But, what has happened is that kp, if kp becomes more negative, if kp somehow becomes more negative, then what will happen? What will happen? Kp becomes, let us say kp becomes, let us say minus 100, then what will happen? E to the power minus of minus 100 minus 1, which is equal to e to the power minus of minus, let us say this becomes minus 100 into this become minus 101 into t, which becomes e to the power 101 t. What is that? It will blow away. It will blow away. It will blow away. Which means if kp is more negative, then error will shoot to infinity. Error will shoot to infinity. Getting my point? Yes. So it means that again it may cause it to be unstable. This is the reason only proportional controller will not help in any manner. But the advantage is that if the open loop system is unstable, then by properly tuning the value of kp, just as we have seen here, by tuning the value of kp, s is equal to 1 minus kp, right? Just by tuning the value of kp, what can be done is you can basically make the system stable. That is what can happen. Okay? Yes, we have seen that. Now let us think of another one. Second type, which is called as integral controller. Integral controller, also given by ki by s. Definitely, if it is integral, then definitely 1 by s has to come, right? Because we have seen that Laplace transform. Laplace transform of, let us say, integration 0 to t f of t dt, if it is there, then it is going to be f of s upon s. We have this idea, right? 1 by s has to be there if it is integral, right? Definitely, that is going to come. Now, case one, let us think of this one. Case one, let us take. Okay, yes, this is the thing. Now, let me consider loop gain. What is the loop gain here? GH, H is 1, it becomes Ki upon S into S minus 1. What do you find now? Initially, the system was unstable. Yes, it was unstable. But now, you have added one more S. Sone pe suhaga. We say that in Hindi, right? S. You have added one more pole at origin. You have added one more pole at origin. Initially itself the system was here. This was it. But now you have added one more pole here at origin, which means you have made it even more worse, even more unstable. right? This is what we have seen, but this is case one. Case one in the sense we have considered original system to be unstable. Now let me take another system which is stable and then try to do the same thing. Let us see what happens. If you see now, open loop system is stable. Okay? Yes. What is the loop gain? What is the loop gain? Loop gain is nothing but GH, which is nothing but Ki upon S into S plus 1. Is that correct? Yes. Now here, even here if you see, because of adding one pole at origin, my stable system has become more unstable. Initially system was stable, yes. But now by adding this integral thing, what has happened? I have added one pole at origin, which means, see here, if initially this was here, I have added one more here. And if you see the root locus will be like this breakaway points and then it will go this way. Getting my point? Right? Yes. So if you check out, this has made it even more unstable. Means it is stable, but still it is trying to make it unstable, right? Now, what is the advantage? What is the advantage? See, it may become unstable, yes, definitely. But what is the advantage? For that, let me think of steady state error. Steady state error ESS. If I think of ESS, what is happening? ESS is what? Let us find KP. Your GH is what? GH is nothing but Ki upon S into S plus 1. Right? What is KP? KP is limit as S tends to 0 GH, which is nothing but limit as S tends to 0 Ki upon S into S plus 1, right? Which is nothing but equal to infinity. So ESS is equal to 1 by Kp, which is equal to 1 by infinity, which is equal to 0. Error is 0. Now let us find Kv. Kv is what? Limit as S tends to 0 S into GH, which is equal to limit as S tends to 0. Yes, definitely. S will be there. Ki upon S into S plus 1 is already there. SS gets cancelled. S into 0, it becomes Ki by 1. Therefore, ESS is nothing but 1 by Kv. So it becomes 1 by Ki. What do you observe? What do you observe? You observe that error has been reduced or not. Because if you think of only this system 1 upon S plus 1 and you try to find, let us say, Kp for this, then it becomes limit as S tends to 0. Limit as S tends to 0. This S becomes 0. You get this 1 by 1. This becomes your Kp, and ESS is nothing but 1 by Kp, which is nothing but 1 itself. But here you have got it to be equal to 0, right? So we have seen that error has been reduced 100%. So advantage is that error is reduced, but it is having a disadvantage of what? Disadvantage that it is trying to make stable system unstable, or rather marginally stable, right? This is the disadvantage. Now let us think of the third type of the controller. What is that? Let us see. Yes, dear. If you see, the third type is a derivative controller, which is also given by KD into S. Correct? Now, how does that look like? Correct? Yes. Now, what is the loop gain? What is the loop gain? Loop gain is nothing but KDS, KDS upon S minus 1. Is that correct? Yes. If you think of root locus, how does the root locus look? Root locus looks like at origin you have got this 0 and here you have got the pole, right? Root locus will be like this. Pole will start shifting here as my k increases to infinity. My pole will start shifting here. What does this mean? What does this mean? My derivative term is making unstable system stable. See, initially this is here only, but as your k increases, this is a root locus. If you think of root locus, right? If my k increases up to infinity, then this one will come to 0. Now just imagine if this 0 was here, then yes, it would have even brought it here closer to the left half of the S plane, right? Which means what? Derivative controllers, they will make unstable system more stable. And even if you see, since I'm talking about increment in k, that yes, k incrementing from 0 to infinity, which means it is going to improve transient response. It is going to improve transient response characteristics. Getting my point? Transient response in the sense what? Percentage mp, tp, tr, td, everything it is going to reduce. Everything it is going to reduce. Getting my point? Yes. Now, but what happens now is, what happens here is, definitely first, second, and third. If you see first, second, and third, that is the proportional controller, then the integral controller, and the derivative controller. If you check out, this cannot be available in their ideal state. I mean to say, you can never have a ideal thing in practice. Ideally, you cannot have only derivative controller. Hence, in practicalities, what we have is, we have pi, we have pd, and we have pid. Getting my point? Yes. Wherein this pi is nothing but kp plus ki by s. Similarly, this pd is nothing but kp plus kds, and this pid is nothing but kp, which is it is having proportional, plus integral ki by s plus derivative, that is kds. Getting my point? Yes. Now, if you think of this pi is integral. We have seen that it is going to decrease the error, integral controller, which means definitely it is going to improve the steady state behavior. Steady state behavior, right? Now, if you think of PD, what is PD? PD will improve the transient response. We have seen transient response, transient behavior. Then, if you think of PID, what will happen? PID will improve both transient and steady state behavior, both. Getting my point? Now, I will try to summarize it. I will try to summarize it. Now, another thing, if you check out, PI is same as lag. PD is same as lead, and PID is same as lag lead. Now I will quickly make a summary table, and that particular summary table is enough in compensators and controllers chapter. Believe me that. Okay? Yes. Summary. Okay. Let me write compensators, controllers. What happens when my compensator is lag? In lag compensator, what happens? Let us see. We have seen that in lag compensator, omega DC reduces, bandwidth reduces, phase margin reduces, gain margin reduces. Right? Similarly, in PI, what happens? In PI, what happens? Transient behavior not good. Steady state behavior improved. Steady state behavior improved. Right? This was about lag. This was about lag. If you check out why I am drawing them in the same graph, because I know that lag and PI are same. Lag and PI are same. Right? Yes. Now, next one is what? Next one is, yes. Now, similarly, if you think of this lag, what has happened? What is the pole zero plot? Since it is lag means lagging. Lagging in the sense, pole has to come first and then 0 has to come, which means minus 1 by alpha tau, and this becomes minus 1 by tau. Simple. That's it. Now, next. Next is lead. What happens in lead? What happens in lead? In lead, omega GC is increased, bandwidth is increased, PM is increased, GM is also increased. Similarly, PD. PD is same as lead only. What is happening in PD? PD. Transient response. Improved. No, steady state is less. Not good. How does it look? It looks like this. 0 and this. Why? Because I need stability. Lead means what? I am stable. Means stability. Moving towards stability. So if I am sitting at origin, definitely I should see 0 first. So it becomes minus 1 by tau and this becomes minus 1 by alpha tau. Right? On the similar lines, you have lag lead, same as PID. Now, how to remember? In lead you see that D comes at last. Similarly, in PD also D comes at last. That's it. Then yes, definitely lag has to be PI and this lag lead is PID. That is a very simple thing. And another thing, if you observe what has happened, in case of lag, everything is reducing, whereas in case of lead, everything is increasing. Decreasing, everything is increasing. So you please take a screenshot of this. This is very, very important. Only based on this particular summary, we can solve almost 90 to 95% of the problems. Okay, thank you.